So today we are ready to begin our study of one-dimensional potentials, and our first example would be the famous harmonic oscillator. Okay, but before I get to that point, I want to make a few remarks about the Hamiltonian and quantum mechanics. So as you know clearly, our first step is to solve the time-independent Schrodinger equation. Okay, usually the position representation. So the time-independent Schrodinger equation is basically H psi equals E psi. Okay, assuming that I'm writing everything in the position representation. Okay, so the question is, how do I write down the Hamiltonian for a quantum mechanical system? Suppose I know what the Hamiltonian is for a classical system. Can I simply change operator? Can I simply change dynamical observables to operators and write down the corresponding quantum mechanical Hamiltonian, right? That is certainly true, but in some cases you have to be a little careful. Okay, so in the case of a simple harmonic oscillator, it is straightforward. Why? Because you know that the classical Hamiltonian is basically p squared over 2m plus 1/2 kx squared, right? So the corresponding quantum mechanical Hamiltonian can be simply written by replacing p by the operator p and x by the operator x. So p squared over 2m plus 1/2 kx operator square, right? So in the position representation, the time-independent Schrodinger equation for the simple harmonic oscillator case would simply read minus h bar square over 2m d square psi dx square, which is the p square over 2m acting on psi part, plus 1/2 kx square psi equals E psi. Okay, so this will be the simple harmonic oscillator in quantum mechanics. But in some cases, which you might also encounter in your study of quantum mechanics, it might not be very straightforward. You have to be a little careful before you write on the corresponding quantum mechanical Hamiltonian. So I'll give you a very simple example. I'm sure you're all looking at, for example, the charged particle moving in an electromagnetic field in an electromagnetism course, right? So let us write down charged particle in EM field. Okay, and you write down the classical Hamiltonian for this object as 1 over 2m p minus EA over c quantity square plus q times the scalar potential phi, right? So this is something you write. If you have not seen this before, p is the free momentum of the particle, A is the magnetic vector potential, and phi is the scalar potential. So how do I write down the corresponding quantum mechanical Hamiltonians? Well, I should not be hasty and simply write HQM as 1 over 2m p hat minus E whatever A over C square plus q phi, because sometimes you have to be a little careful in expanding these. This part is still correct, but sometimes you have to be a little careful in expanding squares. For example, this square, you should not blithely write this as 2p dot a over c. Okay, this would be okay classically, but you are not guaranteed that observables commute in quantum mechanics. In fact, in this case, you would actually find that if you simply write it like this, you would lose one term. So you should expand this properly, and the corresponding quantum mechanical Hamiltonian should be written as p square plus E square A square over C square minus E over C P dot A minus E over C A dot P plus Q phi. Okay, because since P is a differential operator and A is something that depends on spatial indices, P dot A and A dot P are two different terms. In particular, if I multiply this by a wave function psi, P dot A psi and A dot P psi are two different terms. Okay, so I suppose that would make sense to you. So this is one case in which you have to be a little careful in writing down the corresponding quantum mechanical Hamiltonian. The other case in which you have to be a little careful is you have to ensure that the quantum mechanical Hamiltonian is a Hermitian object, right? So for example, If you had a classical Hamiltonian that was something like, let us say R dot P, okay, whatever this is, R dot P, you cannot simply write down the corresponding Hamiltonian quantum mechanics as R operator dot P operator. This would be wrong because this is not Hermitian. Okay, why? Because R is Hermitian, P is Hermitian, but R dot P is not an object that is Hermitian. So you have to properly symmetrize the Hamiltonian, and the corresponding quantum mechanical Hamiltonian in this case would be 1/2 R dot P plus P dot R. Okay, this symmetric combination is indeed properly Hermitian, as you can easily check. Okay, the Hermitian conjugate of R dot P is P dot R. So this whole operator is indeed a Hermitian object. Okay, so writing down the corresponding quantum mechanical Hamiltonian, once you know the classical Hamiltonian, in most cases, if it factorizes very easily as P square plus X square, then it is very straightforward. But in the case where operators do not commute, and if you have things like R dot P, you have to be a little careful and make sure that you're symmetrizing the Hamiltonian and writing down a Hermitian Hamiltonian. Okay, so that is a point that I wanted to make before we begin our study of one-dimensional potentials. Now there is a question. Why are we writing overlap of psi f and psi I as the matrix element representation, or is it just a notation? So I'm guessing that the question refers to this equation that I wrote down yesterday. So basically I'm writing down the amplitude for a system to go from an initial state psi I to a final state psi f. And here I'm simply assuming that I can get to the final state from the initial state by the application of an operator A. That is an assumption. Okay. In fact, it is usually the case. The time evolution is usually generated by the Hamiltonian. So the overlap of the final state with the initial state is simply given by psi I A psi f. That is all. Okay. So assuming that this operator A is Hermitian. So here I'm assuming that there is an operator A that gets me from one state to the other. Okay. So having clarified that, let us move on to our first example that we will study. And the first example is a very famous example. I'm sure you have seen this already before. This is a simple harmonic oscillator. I'm going to be treating the simple harmonic oscillator in terms of what are called creation and annihilation operators, or the ladder operators, and I'm not going to be following the differential equation approach. But for now, let me quickly go through the basics of a simple harmonic oscillator, at least what you understand classically, and then we will try to understand what happens quantum mechanically. So in classical mechanics, a simple harmonic oscillator is one in which a particle is acted upon by what is called the Hooke's law. So Newton's law reads md square x dt square equals minus kx, or I can write this as x double dot. X double dot is a shorthand notation for d square x over dt square plus omega 0 square x equal to 0, where omega 0 square is your frequency squared, which is k over n. And as you can easily guess, this has solutions that are oscillatory. So a cosine omega t plus some phi. Okay, and you fix the constant phi by appealing to boundary conditions or initial conditions. At time t equal to 0, where was the object? And then you simply fix the constant phi based on the initial condition. Okay. And there is also some conservation laws that drop out of this if you look at it carefully. So if I multiply this equation of motion by x dot x double dot plus omega square x dot x equal to 0, then you can recognize that I can write this as d dt of 1/2 x dot square plus 1/2 omega 0 x square equals 0. Okay, this and the first equation, the first line and the second line are the exact same things. If I differentiate x dot square, I get x dot x double dot times 2, and the 2 and the half cancel. Okay. Similarly for the second term. So I have this object inside the bracket whose time derivative is 0. If something's time derivative is 0, it means that that object is constant with respect to time. It doesn't change. So I can identify a conserved quantity in this motion, which is 1/2 x dot square, 1/2 omega 0 square x square, which is a constant. And plugging in omega 0 square as k over m, we see that this is nothing but 1/2 mx dot square plus 1/2 kx square, which is your total energy, is a constant. Okay, there are no frictional forces at play, so the total energy remains a constant for this problem. Okay. So what are the classical turning points? Well, so if I could draw a simple picture of the potential. Okay, so this is my V of x. Now notice that the particle executes simple harmonic motion. So it oscillates from here to there, and so on and so forth. So it reaches some maximum height on both sides, right? Let us call this height as x0. Since this is my 0, this would be minus x0. Okay. And at this maximum amplitude, the energy is E max is 1/2 k, sorry, not E max. There is no maximum energy. Energy is conserved. So E potential, maximum potential energy is 1/2 kx0 square, because at the point where the potential energy is maximum, the kinetic energy is obviously 0. And since energies are constant, the total energy always has to be 1/2 kx0 square, right? So I can write my energy condition as T, the kinetic energy, plus 1/2 kx square equals 1/2 kx0 square, right? Now, why do I call them the turning points? Why doesn't the particle go beyond the turning points? Well, because I can write my kinetic energy as 1/2 kx0 square minus x square. So if x becomes greater than x0, T kinetic energy becomes negative, and since negative kinetic energy does not make any sense classically, x greater than x0 is what is called the classical turning point. X is equal to x0. So the region x greater than x0 is the classically forbidden region. Okay, the particle cannot possibly leak into the region where x is greater than x0. The particle cannot go beyond x is equal to x0. Obviously, the region x less than or equal to x0 is the classically allowed region. So in your study of classical mechanics, these are the two regions you investigate, and you try to understand how the dynamics looks like. And the dynamics here is very straightforward. It's just oscillatory motion. Okay. So how does this picture emerge in quantum mechanics? What happens in quantum mechanics? Does the particle not go into the classically disallowed region? Well, let us investigate. So before I begin the quantum mechanical description, are there any questions about the simple classical picture? You can always unmute and ask if you have any questions. Okay. Okay. So the Hamiltonian is p square over 2m plus 1/2 kx square, right? So I'll write down the time independent Schrodinger equation in the x representation. D square psi dx square plus 1/2 kx square psi equals E psi. Now I'm not going to solve this differential equation. Instead, I'm going to assign the solving this equation, differential equation part, as a reading, because otherwise it will become an exercise solving a differential equation. And this the method of solving this differential equation is readily available to you by means of what is called the Frobenius method. It's a series solution method. You simply plug in and figure out the recursion relations between the constants, and we can figure out what the series is. And it turns out that the solutions are what are called Hermite polynomials. This is pretty standard textbook stuff, so I will not repeat this in this lecture, we will get to the wave functions in a slightly different way. But now I simply want to understand the limiting cases. I want to understand what happens in the classically disallowed region and the classically allowed region, at least qualitatively. Okay. So it's a very simple description of the quantum mechanical picture before we move on to the creation and annihilation operators. Okay. So let's rearrange this equation. D square psi over dx square, which I will call psi double prime, can now be written as minus 2m over h bar square e minus 1/2 kx square times psi. Okay. So this is simply the same equation rearranged in a different form. Okay, so let's look at this equation. So what is the classically allowed region? The classically allowed region is e minus 1/2 kx square greater than 0, right? This is x greater than x, sorry, this is x less than x0. The classically allowed region is one in which this quantity is positive for all values of x. So no matter where the particle is, as long as it's inside x is equal to x0, this quantity e minus 1/2 kx square is greater than 0. This is obvious because E is the total energy. 1/2 kx square is the potential energy at any particular point. And since the total energy is a sum of potential plus kinetic energy, this simply means that the kinetic energy is greater than 0. Kinetic energy greater than 0 is the classically allowed region. Right? So psi double prime in this case is equal to, so I'll write this as some minus k square as a function of x times psi. Again, my goal is not to solve this differential equation, but just to tell you what happens qualitatively. Okay, so obviously you can clearly guess that the solution here in the classically allowed region would be oscillatory. Because this is simple harmonic equation. So this will be some e to the ikx, e to the minus ikx kind of deal. Okay, somewhat. So you might be a little confused because this k square is not a constant here, it's a function of x, because this is not strictly speaking a simple harmonic equation. It is e minus 1/2 kx square. There is an x dependent part here also. But again, my goal is to sort of qualitatively describe what's going on. They should be greater than or equal to an energy case and x less than or equal to x0 position. All right. X less than or equal to x0 is the classically allowed region. Okay. It can be at x0 because at x0 the potential energy is maximum. Very good. All right. So now what happens quantum mechanically in the classically forbidden region? Classically forbidden region this is where the kinetic energy is negative, right? So classically, this is x greater than x0, plus minus x0. So if I look at this equation again, I can write this as psi double prime equals 2m over h bar square times 1/2 kx square minus e times psi. Okay, and I'll call it some kappa square, again as a function of x. So psi double prime is some kappa square x times psi. Okay, so the solution in the classically forbidden region is not oscillatory, because oscillatory means there should be a negative sign in front of the kappa square. Since there is no negative sign, this is not oscillatory. So the question is there a solution at all, right? Because classical mechanics tells you that the particle can never be found outside x is equal to x0. Quantum mechanics tells you that the wave function can be found outside x is equal to x0. So what is the corresponding wave function? Again, I'm not going to solve this differential equation, which you should solve, but I'm simply going to look at the asymptotic limit. what am I going to do? I'm going to look at the extreme case where it is not at all classical. Asymptotic limit is when the kinetic energy reaches a maximum negative value, which doesn't make any sense classically. So I'm going to look at the region where the potential energy 1/2 kx squared is much greater than the total energy E. In other words, the kinetic energy is a highly negative quantity. So what is this region? In this region, the equation becomes in the equation in the blue box, so or the green box, which is this. If 1/2 kx squared becomes much larger than E, I can simply neglect E in comparison to 1/2 kx squared, and I will write this equation as the two things cancel. So this is mk over h bar square x square psi, but k is just m omega square. So I can write this quantity as m omega 0 square, m square omega 0 square over h bar square x square psi. Okay. Psi double prime equals m omega 0 over h bar quantity square x square psi. So there is a quantity that appears which is called m omega 0 over h bar the whole square. Okay. So there's a question. When in the postulates of quantum mechanics is this case that particle can even have negative kinetic energy to even consider calculated in the case as opposed to classical mechanics? No, this does not mean that if you measure the kinetic energy of the object, you will get a negative number. That is not what it means in quantum mechanics. The interpretation of this I will talk about later. Okay, so for now, simply understand that even in a classically forbidden region, the particle's wave function is not necessarily zero. If the wave function is not necessarily zero, then psi square dx is not necessarily zero. And since psi square dx is a probability of finding the particle, the probability of finding the particle in a classically disallowed region is not necessarily zero. Okay. So when we talk about tunneling, I will explain this in a quantum mechanically sort of obvious way. But for now, simply understand that even in a classically disallowed region, there can be cases in which the quantum mechanics allows the particle to propagate. Okay? But it is a highly decaying function, as I will demonstrate. So the asymptotic limit when 1/2 kx squared is much greater than E, you would actually find that yes, the wave function is non-zero, but it is also decaying very fast. Okay. So what is this quantity m omega 0 over h bar? Okay, m omega 0 square. So prove or demonstrate, which is very easy, demonstrate that m omega 0 over h bar has units inverse centimeter. Okay. So it can be understood as some kind of a wave number if you want. So I'll call beta to be beta square to be m omega 0 over h bar. So I can write this equation in the asymptotic limit as, again, this is stopped showing. So let me reshare my screen. So psi double prime can be written as beta to the 4th x square psi. Okay. So you might be wondering why I write it as beta square instead of beta. That should be clear in just a second, where I do a change of variables. So I'll do a change of variables from x to some c, which is beta times x. Okay. And in terms of c, you can easily show that the equation transforms to d square psi over dc square equals c square psi. Okay. So this is the Schrodinger equation in the region 1/2 kx square is much greater than E. Or if you look at this picture, this is, where is the picture? This is the picture. I'm looking at the solution over here and over there, like far up, far to the left and far to the right. Regions where classically you never expect the particle to be found. Okay. All right. So now, what is this solution to this equation? Well, you can easily demonstrate to yourself that the solution in this case would be exponential plus minus c square over 2. Okay. If you doubt this, you simply plug this back here, plug, and check if this is a solution. Okay, this is something you should do. So in the region where in classical mechanics the particle can never be found, the wave function in quantum mechanics, by solving the one-dimensional Schrodinger equation, time-independent Schrodinger equation, we get psi as some a e to the minus c is beta times x, so beta square x square over 2. Okay. So of course, as x becomes very, very large, this goes to 0 on both sides. So obviously, the particle can, so, okay, plus minus, right? Sorry, I missed this point. Plus minus. Now I want the wave function to be normalizable. If the wave function is to be normalizable, I cannot take the e to the plus sign. So I require psi to be normalizable, right? In other words, I want minus infinity to infinity psi star psi dx to be 1. But if I take the solution e to the plus beta square x square, there is no way this wave function will be normalizable, because as x goes to plus minus infinity, this blows up. So the physically acceptable solution is psi of x equals a e to the minus beta square x square over 2. In the region 1/2 kx square is much greater than. Okay, classically forbidden region. All right. Okay. So this is how you sort of understand things in a qualitative picture. Let us recap some of the important elements of this calculation that we have done. Excuse me. So the first lesson that we have learned is that, as someone correctly pointed out, the wave function does not simply become 0 in the classically forbidden region. So there has to be an explanation as to what this means, and we will talk about the explanation as to what this means in the subsequent classes. Tunneling is a very peculiarly quantum mechanical phenomenon. Okay, tunneling is actually a very important phenomenon in which the particle, even though it doesn't have enough energy to climb over a potential, can still leak outside, and there is a finite probability for it to be found outside. Okay, see, classically, there is no way for the particle to leak outside x is equal to x0. It's always found inside x is equal to x0. In quantum mechanics, there is a finite probability for the particle to leak outside x is equal to x0. Okay, and somewhat counterintuitively, when you study quantum field theory, you again find that the tunneling amplitude is again 0. Okay, so in classical mechanics there is no tunneling. In single particle quantum mechanics there is tunneling, and in quantum field theory, again, just like classical mechanics, there is no tunneling. So this is actually a very nice feature of how various physical theories and various scalings behave. Anyway, and so what we then understood is what is the wave function of the particle, or how does it look like in the classically forbidden region. And to understand the classically forbidden region, we took the asymptotic limit where the potential energy is much greater than the total energy. Okay, this is the classically forbidden region. And we took the extreme case of 1/2 kx square is much greater than E. We rewrote Schrodinger equation in a much simpler form, and we found that the solutions are e to the plus minus x square. And e to the plus x square we threw away because that solution is not normalizable. This is the difference between doing mathematics and doing physics. Even though a second order differential equation has to have two linearly independent solutions, as your mathematical physics instructor should tell you, In physics, you can always throw away one or the other because it is not physically reasonable. Okay, this is what you do, for example, in electromagnetism also, many times when you solve the Poisson equation. Okay, so this is how far we can get by cheating, right? Without actually solving any hard differential equations. This is as much as we can do. So enough of cheating, and now let us actually do some honest work. And before we start doing, are there any questions? Any questions or comments about any of this? You can also unmute and talk if you want. If I measure the position of the particle, can I ever find that the particle is in the classically forbidden region, or I'm just getting the probability of finding it there? Very good. No, the probability of finding there is actually a physical thing. So when I say that the probability of finding it there is non-zero, it means that there is a finite chance for you to find it there. Okay. So if it is a truly quantum mechanical particle confined using a potential kx minus kx, which is a bound system, then it is quantum mechanically possible for the particle to leak outside the classically allowed region. Okay. So this is not just a mathematical trickery. It simply means that if you're an experimentalist and if you measure, you would actually find that there is a non-zero probability for the particle to be found outside the classically allowed region. Okay, that is what this means. If psi square dx is not zero outside, that's what this means. Of course, the probability would be very small. And as you keep going away, farther and farther away from the turning point x is equal to x0, the probability would also keep dropping. It will become smaller and smaller and smaller, but it is there. It is non-zero, which means 1 out of a million times you would actually find the particle somewhere very far away from the classically allowed region. So this is an experimental fact, absolutely. Any other questions? Okay. The Hamiltonian for the harmonic oscillator is a very special case. Okay. This is a very special case. Oh man, this is again not showing. I'm so sorry. Okay. Because it is a sum of squares. And because it is a sum of squares, it invites us to do the calculation in a slightly different fashion. Okay. So what I'm basically going to do is use the very complicated formula: a square minus b square is a plus b times a minus b. Of course, you might object saying that there is no minus here. It is p square over 2m plus 1/2 kx square. But that doesn't stop me because I can always write this guy as, let's say, 1/2 kx square minus ip square over 2m. Right? I can always do this. And this is of the form a square minus b square. So I can always write this as a plus b times a minus b. This is an example of what is called a factorizable Hamiltonian. And these are extremely rare to find. Okay, so these are very precious beasts. So you should, whenever you find one, you should beat it to death. So you should understand everything about it. That's why physicists are obsessed with harmonic oscillator. It's actually a very simple system to study. It's also a very important system to study. It turns out that the universe is fundamentally composed of harmonic oscillators. It's an extremely important system to study at every stage of your physics education. So this invites us to factorize this Hamiltonian in terms of something that corresponds to x plus ip and something that corresponds to x minus ip. The exact operators that we will use are A, which is the combination x plus ip, x plus, in fact, it is ip over m omega 0. And remember, sorry, and A dagger, the Hermitian conjugate of this operator, which is x minus IP over m omega 0. Obviously, A is not a Hermitian operator because A dagger is not equal to A. Okay. Obviously, A and A dagger do not commute because they are composed of X's and P's, and X's and P's don't commute, so we cannot expect A and A dagger to commute. So since we are dealing with a sum of two squares, we can factorize the Hamiltonian in terms of A and A dagger, and we have to understand what A and A dagger mean. We will understand them in a second. But first, let us write down what A and A dagger are and what their commutation relations are. So remember that my beta is, right? So I defined it over here when I introduced the length scale of the problem. This is a length scale of the problem. Okay, there is a fundamental length scale. This is actually quite important in physics because given you have been given a system, right, and you are given some constants. So you should always try to see if you can take some combination of the constants so that you can find a length scale for the system. Okay. In this case, there is three quantities available. H bar because it's a quantum mechanical system, and the mass of the oscillator is given, and the natural frequency of the oscillator is given. So it turns out that if I combine these three parameters in the ratio m omega over h bar, I get a fundamental length scale 1 over centimeter, or h bar over n omega would be a centimeter. So for those of you who are interested, suppose instead of x square potential, I have a 1 over x square potential. Okay. And you try to understand what is the fundamental length scale. So 1 over x square should also be a factorizable Hamiltonian, right? Because x square is a factorizable Hamiltonian. So 1 over x square should also be a factorizable Hamiltonian. And write down what is the corresponding length scale of this potential. And you wouldn't be able to do it. Anyway, that is for people who are interested. Let us come back to this particular system. So let us first calculate the computation of A and A dagger. What is the computation of A and A dagger? Now both of them come with a factor of beta over 2, so I can factorize a beta square over 2, and this will be the combination of x plus IP over m omega 0, comma x minus IP over m omega 0, right? Now x and x commute, p and p commute, so the only non-commuting things in this are x from here and minus IP from here, and IP from here and x from there. That is all. So for those of you who are not comfortable with calculating commutation relations of combinations of objects, please pay attention and ask me if there is any questions. So this is beta square over 2 times, the first commutation is minus I over m omega 0 times the commutation of x and p, which is IH bar. Sorry, this is not a comma, this is plus. This is a comma, this is a plus. Plus, the second commutation relation is I over m omega 0 times the combination of p and x, which is a minus IH bar. And using the definition of beta square, you can actually show that this is equal to 1. So the commutation of A and A dagger equals 1. So A dagger minus A dagger A, which is the commutation of A and A dagger, equals 1. So this is a fundamentally important commutation relation, simply because A and A dagger are composed of X's and P's, and it is basically the commutation of X's and P's. Okay. So using this, I can rewrite my X's and P's as X is equal to, remember that A is an addition of X and P, and A dagger is a subtraction of X and P. So if I add A and A dagger, I get X, and if I subtract A and A dagger, I get P. So X can be written as 1 over root 2 beta A plus A dagger, and P can be written as m omega 0 over I. This is all very simple algebra, so I'm not going to derive it in detail, but I will let you check it. Check. Whatever I write in blue, you should always check. So let's substitute this. Sir, can you explain how did you establish this commutation relation? Okay, very good. So I want to calculate A dagger commutation, right? Now what is A? A is, the way I have defined it, is beta over 2 x plus IP over m omega 0, and A dagger is beta over 2 x minus IP over m omega 0. Okay. So there is 4 commutation relations here. So there is a beta over 2 here, beta over 2 here. So beta square over 2 I'll pull out. The first commutation relation is the first guy over here and the second guy over here. So the commutation of this with this, and the commutation of this with this, and the third guy is the commutation of this with this, and the fourth guy is a commutation of this with this. Okay. So the first guy is x comma x, which is obviously 0. The second guy is x comma minus IP over m omega 0. The third guy is plus IP over m omega 0 comma x. And the fourth guy is IP over m omega 0 comma minus IP over m omega 0. But p commutes with p. So this is 0 and this is 0. And I know that the commutation of x and p is IH bar. So if you substitute this, you will get A dagger commutation is equal to 1. Is that clear to everybody? Yes? No? Okay. So using this, I can now rewrite my Hamiltonian. So what is my Hamiltonian? My Hamiltonian is p square, which is 1 over 2m. And this becomes a minus m square omega square 1 over 2 beta square. Now again, when I square it, I have to be careful. When I square a minus a dagger whole square, I should not write a square minus a dagger square minus 2a dagger. I should write this as a square plus a dagger square minus a dagger minus a dagger a, because a and a dagger do not commute. That is my p square over 2m plus 1/2 m omega square x square, and x square would be 1 over 2 beta square a square plus a dagger square plus a dagger plus a dagger. Okay. Now, if you plug in the value of beta square, which is m omega over h bar, you would actually find that the a square and the a dagger square should cancel. And again, this is something you should check. Assuming that I've done all the algebra correctly. And your Hamiltonian can be simply written as h bar omega 0 times a dagger a plus 1/2. Okay, now you might object saying that, look, there is also an a dagger a piece and an a dagger piece here, right? But notice that I can always use the fact that the combination of a and a dagger is equal to 1. So my a dagger piece, a dagger, can always be written as 1 plus a dagger a. So these are not two separate terms. I can always write one in terms of the other. So if I use this, I will get my Hamiltonian as h bar omega 0 times a dagger a plus 1/2. Okay, so this is a very important Hamiltonian. This is the Hamiltonian for the simple harmonic oscillator written in terms of the a operator and a dagger operator. So again, the reason I introduced a and a dagger, I could have simply written, went ahead and solved this differential equation. But the reason you do this is because it is physically much more intuitive. this way of doing the simple harmonic oscillator. I will never do any other problem because all other problems that we will do in this course are not factorizable Hamiltonians. Only the simple harmonic oscillator is a factorizable Hamiltonian. Okay. So notice that again, I have not done anything. I have simply rewritten my time-independent Schrodinger equation, which is h psi equal to E psi. So the job of finding the eigenvalues and eigenfunctions of the Hamiltonian operator is now boiled down to finding the eigenvalues and eigenvectors of the A dagger A operator. So let me give this a special name. I'll call this A dagger A operator as N. And the reason I call this N would become apparent as we go along. So I can write this H as H bar omega 0 N plus 1/2. So if I find out the eigenvalues and eigenfunctions of N, I have found out the eigenvalues and eigenfunctions of H because the eigenvalues of H is simply the eigenvalues of N plus 1/2 H bar omega. That's all. So let us write down the eigenvalues and eigenfunctions of the N operator. So eigenvalue problem of H, which is H psi equal to E psi, is equivalent to the eigenvalue problem of N. Okay. So let's write down the eigenvalue problem for N. So I'll write N phi N equals N phi N. I'm going to assume that there is a whole bunch of eigenstates, eigenfunctions, phi, each characterized by some number N, which I'm not saying is an integer right now, and the eigenvalue I'm calling it as N. It will turn out that N is indeed an integer, but right now I do not know what N is. And my job is to figure out what the eigenvalues and eigenfunctions of this operator are. Okay. Once I know that, I know everything about the Hamiltonian. I know everything about the solutions of the time-independent Schrodinger equation. And then I know trivially what the time-dependent Schrodinger equation solutions are. Are there any questions about any of this up till this point? This change of variables, this rewriting of the Hamiltonian, this factorizable Hamiltonian idea. Are there any questions or comments about any of this before we move on? Okay. So if there is no more questions, I want to understand a bit more about this N operator. So right now we have three operators, right? We have the A operator, we have the A dagger operator, and then we have, oh, sorry, I have to reshare again. Hopefully for the last time today. Okay, we have the A operator, we have the A dagger operator, and we have the N operator, which is equal to A dagger A. Okay, notice that A dagger A will not commute with either A or A dagger. The N operator will not commute with A or A dagger because A and A dagger don't commute and N is made up of A dagger and A. It is obvious that NA will not be equal to 0. Okay. In fact, we can compute what NA is very easily. What is NA? NA would be A dagger A. So this is equal to, I can write this as A dagger AA plus A dagger A. The first term is obviously 0 because A commutes with itself, and the commutation of A dagger and A. So where here, since the commutator of A dagger is 1, the commutator of A dagger A is -1. So this is minus A. Okay. Similarly, if I calculate N A dagger, that will be equal to A dagger A dagger. This is nothing but plus A dagger. Okay. Now, notice that the eigenfunctions of n will not be eigenfunctions of A or the eigenfunctions of A dagger. Okay, because n and A don't commute, the eigenfunctions of n will not be the eigenfunctions of A dagger. If n and A commute, then obviously n and A dagger would have the same eigenfunctions. But since they don't commute, the eigenfunctions of n will not be the eigenfunctions of A dagger. So tomorrow we will understand how to connect these two. How does A act on the eigenfunctions of n, and how does A dagger act on the eigenfunctions of n? And based on how they act on the eigenfunctions, we would be able to figure out what their physical meanings are, and then the whole picture becomes very, very simple and easy. Since we are running out of time, I don't want to do this calculation now. For today, we'll stop at this point. Tomorrow, we will continue the discussion of harmonic oscillator. We will try to discuss the physical meanings of the A and A dagger, and then finally we will derive the wave functions in the position basis. Okay, so I'll stop here and ask if there's any questions.